Wow. I forget on YouTube that you actually have to hit start stream in two places. Um Oops. So sorry about that. As I was apparently talking to myself, got a little bit of a late start this morning. Um so give me one moment to get a cup of water real quick and then we'll get started. Okay. So I did update all this. That's the right link. That's the right link. Okay. So let's go ahead and get started here. Let's get rid of this countdown. So today we're going to do some cylindrical and spherical coordinates. And I realized the problem set for today still says April 9th. That is a mistake. Oh no, it was 8th and I changed it to 9th even though today's the 10th. That's what happened. That's fine. Oh, also camera. Oh, camera. Hello. All right, so let's go ahead and get started with these. I only got 4 problems on here today. We'll see how that goes. So problem 1. Problem 1 here is just, here's an integral, compute it. So 0 to square root 2 root 2, integral from minus square root of 8 minus x squared to square root of 8 minus x squared, and integral from minus 1 to 2 of square root of 1 plus x squared plus y squared, dz dy dx. Right? So, believe it or not, this is an integral we could do in Cartesian coordinates. It would be, the z integral would be pretty simple. But from the y integral onward, we'd have to use some tricky techniques. We'd have to use a trig sub, and we would have to use a, and the x integral would be even harder. So we don't want to go down that path. Okay, so what do we want to do here? Well, let's figure out the region that we're integrating over. All right. So let's see here. So here we have that x is supposed to lie between 0 and 2 square root of 2. Okay. Here we have y is meant to lie between negative square root of 8 minus x squared and square root of 8 minus x squared. And z lies between -1 and 2. So the question is, well, what is this shape? Right? So let's just ignore z for the moment, and let's just focus on the x and y region, right? Because this is going to be sort of the shadow of our shape. Right? If we just focus on the x and y region, right? What this here is telling you, if you pick either equation here, and you're basically being told that we're inside this circle right here, right? The bottom bound for y is the bottom half of the circle. The top bound for y is the top half of the circle. So we're saying we're inside this circle. So let's graph this. Radius of the circle, by the way, is 2 square root of 2. So here, let's graph our, let's just say this is 2 root 2, 2 root 2. Maybe these are the negative ones. And so here's our circle. This is probably the best circle I've drawn on this tablet yet. Right? So there's the y bounds, right? The top one is up here, the bottom one is down here. Now the x bounds here, these say I'm between x equals 0 and x equals 2 root 2. Right? So I'm only actually interested in this half of the circle here. Right? So that's my shape here. Right? But now we want to add z into the mix. So now that we know what the x and y's look like, we can just use the fact that, well, z goes from -1 to 2. So all that means is you have this shape and it starts down at z equals -1 and goes up to z equals 2. So if we draw this in 3D space, hopefully my picture isn't going to be too bad here. We're going to end up with something like this. Probably more like that. This is hard to do. Okay. I'm very bad at doing this. But what we have is kind of like a half of a cylinder of height 3, basically. So imagine a nice round cylinder cut in half a long ways. And it has height going from -1 to 2 on the z-axis. Kind of hard to draw. At least hard to draw for me. So this, let's call this region D. Then we can describe the region D in cylindrical coordinates. That's a piece of a cylinder, so cylindrical coordinates should be the go-to here. D, in terms of r theta z, right? The cylinder has radius 2 root 2. So r goes from 0 to 2 square root of 2, right? Theta here, so we can find theta in the xy plane here. It's got to start down here and end up there. Since we want to go from the negative y-axis to the positive y-axis, this is just going to be minus pi over 2, right? And then the nice thing is z actually never changes from Cartesian to cylindrical. So all we have to do is just write the same bounds for z. Right. Sorry, sketching these things is not my strong point here. Right. But hopefully this makes sense what we're looking at. So again, we have a nice circular cylinder that's been cut in half long ways. And the bottom part of the cylinder is at z equals 1. The top part is at z equals 2. Okay. So that means we need to switch this integral. So let me call this integral I, so I don't have to rewrite that whole thing. Okay. So I. All right, let's set up the bounds first. All right. Now, setting up the bounds is pretty easy. We have them all written right here. So we can do this in basically whatever order we want. We can actually keep the z bounds exactly the same because, again, z doesn't change. So we'll do dz first. All right, now remember though, when we're switching from Cartesian to cylindrical, just like with polar coordinates, there is an extra r that comes with it, all right? Because it basically is polar coordinates plus z. Right. And then we'll do dr d theta next, since that's our sort of usual order for polar. All right, so let's see, r will go from 0 to 2 root 2. Theta will go from minus pi over 2, pi over 2. Right? Now, what does this thing in the integrand become up here? Right? Well, again, we would convert this in the exact same way we convert things to polar coordinates. Right? So x squared plus y squared is r squared. So this turns into square root of 1 plus r squared. Right? This should look very familiar. Okay. Okay. So now it's just up to us to compute this. All right, so when we integrate this with respect to z, we're just going to get 3 in there. Right, so that's all we're going to have. When we integrate this one's going to be done with a u substitution. Okay. So pi over 2 to pi over 2. The u sub you would make here is 1 plus r squared. So let's see here. We get 3. Oops. 3. Let's see, we integrate that, we're going to get 1 plus r squared. Times 2/3, and then from du, we're going to get an extra 1/2. All right, d theta. Nice thing here is those 2's cancel and these 3's cancel, so these all go away. Oh, we have to evaluate this from 0 to 2 root 2. Right. So let's see, minus pi over 2 to pi over 2. So this is going to be square root of 1 plus 8 minus square root of 1 plus 0 d theta. So what we're looking at here is the integral from minus pi over 2, pi over 2. This is square root of 9 minus square root of 1, so 3 minus 1. This is 2 d theta. And so this integral is going to end up being 2 pi. Right? Again, the actual computation is less interesting here than being able to switch it to the correct coordinate system. But again, also, the benefit of different coordinate systems is that it sort of allows you to simplify integrals into a form that you're able to compute. Right? Sometimes it's also just easier to describe your integral in terms of these coordinates as well. Because remember, even if you're, just taking the approach of, I'm going to drop all of the integrals I need to compute into Mathematica or, some similar program, you still have to be able to tell the program, well, what function am I integrating? What region am I integrating over? Right? And sometimes describing these regions is just easier in these other coordinate systems. Okay, so let's go ahead and look at the next problem here. So the next problem, problem 2, is we want the volume of the region bounded by the cone and the paraboloid 12 minus x squared minus y squared. Okay. So this region here, I think we had something a little similar actually when we did polar coordinates. I think these were in the opposite order. The cone was going down and the paraboloid was going up. But here we'll see that this stuff is really easy to set up when we're just doing things in triple integrals, right? So first things first here, we should figure out, what is the solid look like, right? So a rough sketch of this. Let's use blue and pink, I suppose. I'm going to draw the shapes without the axes first. So this cone right here looks something like this. Okay. So there's our cone. The paraboloid is going to start up here somewhere, and it's going to go down. Right, and the important, oops. It was just a bad drawing. This. Right, so we want to look for where does this paraboloid hit the cone at. So you kind of have this, bell shape going down and a cone going up. So you have a pointy end on the bottom and a round end on the top. We want to figure out, well, how do we integrate over this? Well, the nice thing is the z bounds are going to be quite easy to figure out. It's the other things that we need to sort out, right? So you might remember how we did this last time. Once we set the z integral, we're going to be looking at the shadow of this shape in the xy plane, right? So we're going to need to do something similar to what we did last time. So here we need to figure out, since the intersection here is the widest part of this shape, we need to figure out what that intersection is, right? And to do that, we're going to try and plug one equation into the other. Now, there's a couple options for this. We could say, oh, this is a z, this is a z, so let me set them equal like that. Now, you could do that. Let me slightly advise against that, because that'll be a bit tricky to deal with. Instead, let me suggest solve this equation here for x squared plus y squared. Right, so this will be 12 minus z. And now I can take that and plug it underneath the square root there. Okay. So we have z equals square root of 12 minus z. Okay. And now we can square both sides. So z squared is 12 minus z. And this is, actually, let me do this on the next line. Move this stuff over, z squared plus z minus 12. And we can factor this as z plus 4, z minus 3. Right. So here, this one says z is negative 4. This one says z is 3. So how do we know which one to use here? Any suggestions for how we might know which one to use? I'll give you a second to think about it. Right. So it's got to be this one, z equals 3. And the reason is, z is the square root of x squared plus y squared, which means that z has to be positive, right? And if z is positive, well, this is the positive answer. So the reason this one shows up is since we squared this equation here, we actually end up with solutions for the full cone. The full cone has the part on top and the part below. So z equals negative 4 is where that paraboloid hits the bottom part of the cone that's opening up, right? If you square both sides of this equation up here, of this one, go away, of this equation here, you square both sides and then graph it, you get the double cone going up and down. All right. So z equals 3 is that. So if we plug that into either equation here, what we're going to find out is sort of the boundary is x squared plus y squared equals 9. Right, so this is going to be the shadow in the xy plane. Okay. So now we kind of have an idea of what the shape looks like. Actually, hold on. We're not doing this in cylindrical coordinates, are we? Oh no, we are. We are. Okay. No, we're good. All right. Sorry. So now that we have that, now we can set this integral up. I didn't put that in the problem, did I? I meant to say do this with cylindrical coordinates. All right. So doing this with cylindrical coordinates, so we need this for the r and the theta. This picture tells us the x and the y, or sorry, the z situation. So the volume will be, actually let me say, remember that volume is always triple integral of dv. Okay? And in this case, maybe I should do this on the next line. I can fit it here. I just am not zoomed in or zoomed out so far. Right? So here, when we switch, we're going to get r, and then, you know, we want some order of integration here. Z should come before r at the very least. And since we usually put theta last, let's go ahead and do that. So if we look at the shape here, we need to figure out, well, what do these bounds turn into? The cone is on the bottom, so that's just z equals square root of r. The top is this paraboloid here, which is 12 minus r squared. Right? Because again, x squared plus y squared is r squared. R, if we look at where the shadow is going, r is going to go from 0 to 3. And here, since we have the full sort of 2 pi rotation of this shape, this is going to go from 0 to 2 pi. And there we go. That's setting up this volume in cylindrical coordinates. Right? Let me say real quick, this problem works a little bit better in cylindrical than spherical because of the lack of a z-squared here. Right? Now, I'm not saying it's impossible to do this in spherical coordinates. In fact, it's actually probably not that bad. So, what the heck? Let's set up the integral in spherical coordinates as well. It'll be a nice transition. So, if we're going to do this in spherical coordinates, we need to think about, well, what do these equations turn into? Okay. So, for spherical, right, this cone right here, is the nice 45-degree cone, right? So this one, all it's going to turn into is phi equals pi over 4. All right? That's this cone. Now, this shape is a little bit different. Right? We have to remember, what does x squared plus y squared turn into? Right? Well, it's going to turn out to be 12 minus rho squared let me remember this. Sine squared phi. Yep. Right? Why is that true? So x squared plus y squared. If we switch this to spherical coordinates, we get rho squared cosine squared theta sine squared phi plus rho squared sine squared theta sine squared phi. So here, if we can factor out this stuff, that was supposed to change color. We can factor out the rho squared sine squared phis. And we're just left with cosine squared theta plus sine squared theta. And we know that's equal to 1. So all we're left with is this. Right? So that's this up here. So if we want to reintegrate this shape in spherical coordinates, if we wanted to set up the bounds there, the volume is, so we're still looking at triple integral of dv. Right? See. So we need to decide on some order of integration here. So remember dv, what does that turn into? Rho squared sine phi. D here, we'll want to integrate d rho first. And then is that right? Yeah. D rho, let's say d theta d phi. Right. Let's see. Is this a wise choice? This paraboloid's actually going to be a little tricky. I wasn't planning on doing spherical coordinates for this. I'll have to think about it a little bit. We might not actually want to try this in spherical, because this paraboloid equation is rho cosine phi equals 12 minus rho squared sine squared phi. And we'd have to solve this for rho, which doesn't look super fun, to be honest. So actually, let me just punt this and say, not a great idea. Whereas, if we look at this in cylindrical, this becomes pretty simple. Right? So, yeah, I guess let me point out here that, not all coordinate systems are right for every integral. Right? Since we have a lack of a z-squared term in this paraboloid here, things become a little bit tricky. And so setting up the bounds in spherical is actually going to be kind of hard. Right? So, you really want to think about what your shape looks like, what kind of equations are involved in it, and using that, you can get to a simpler solution. Okay. So that's an enlightening detour. All right. So let's go on to the next problem. All right. Sorry. In the next problem here, oh my god. Wow. All right. So the next problem, we're trying to evaluate this integral dv, where d, this is the region in the first octant, and between the spheres x squared plus y squared plus z squared equals 1, and x squared plus y squared plus z squared equals 2. Right? So we're saying between the two spheres of radius 1 and 2 centered at the origin. Right? So the fact that this problem has a whole bunch of spheres in it sort of screams use spherical coordinates, right? So let's go ahead and do that. Sorry. Okay. So, these two spheres here, this one is rho equals 1. Sorry, this is supposed to be a 4. This sphere of radius 2 is rho equals 2. So the rho bounds on this are actually pretty straightforward. So again, let me call this thing I so I don't have to rewrite it. All right. So let's start changing this integrand here. Right. So this stuff right here, remember, x squared plus y squared plus z squared, that is rho squared. So this is rho squared with a minus 3 halves. And then dv, remember, is rho squared sine phi. And then let's integrate in the order d rho, d theta, d phi. Okay. So our rho bounds are given right here, 1 to 2. Right? Because we start on the inside at a sphere of radius 1, and we go to the outside at a sphere of radius 2. So, when you're thinking about how rho works, you want to think about it just like the same way that r worked in polar coordinates in the 2D plane. Rho is just the 3D version of that. It starts at the origin and it works its way out, but it can move in sort of any direction away from the origin. Okay. So now let's think about the rest of this shape, right? So we're stuck between these two spheres, right? The rho keeps us between them, but now we're stuck in the first octant as well. So how do we set up those bounds? Right. Well, the first octant right? So here we have all of x, y, and z being positive. Right? So think about the first octant. What part of the xy plane is that? Right? That's the first quadrant of the xy plane. And to stay in the first quadrant, theta has to measure from 0 to pi over 2. Right? So we stay in that first quadrant there. Right? And phi, remember how phi works. Phi sort of starts all the way at the top and measures downward. Right? So it starts up here at 0, and then it falls. Okay? So that means phi is going to go, also from 0 to pi over 2. Right? So again, if it's 0 at the very top, then by the time you tilt to pi over 2, you're in the xy plane. If you go any further, you're going to leave the first octant. So in both cases here, we have 0 to pi over 2, 0 to pi over 2. Right? And then that's all there is to it. Right? So I think I'll stick with just setting up this integral here. Maybe we can simplify it a little bit. Right? So 0 to pi over 2, 0 to pi over 2, 1 to 2. We simplify this part. This is going to be rho to the negative 3 times that rho squared gives me rho to the minus 1 sine phi. D rho, d theta, d. Right? So some pretty interesting stuff there. All right, so this integral's not too bad to compute at this point, so I think I'll leave that to you. And we'll just move on to the last problem here. Because again, setting up these integrals, this is the most important part. All right. Since we only have like 5 minutes left, probably a good idea. So here, I want to look at, in problem 4, I want to look at a different region here. I want it to be inside both of these spheres. Oops. Right? So I want the region inside both of these. So how do we figure this out? All right. Oops. Sorry, my desk is a little falling apart here, apparently. All right. So easy enough. We need to switch these to spherical coordinates. This is a sphere of radius 1, so this is just rho equals 1. Or sorry, I should say sphere of radius 1 centered at the origin. Now, what about the other one? We have a little work to do. So this other equation let's expand out this term. Okay, so we get this right here. Okay. And then notice this part right here is rho squared. So we get a rho squared. Now here, 2z, well, there's not much we can really do about that. So this is 2 rho cosine of phi, right? Oh, this is plus 1, sorry. And this is minus. I can't multiply today. I was looking at that thinking like, that's not going to come out right. All right. So now we have this equation. Let's try and solve this for rho. So these ones are going to cancel. And I can divide by rho here. So I get rho minus 2 cosine phi equals 0, or rho equals 2 cosine phi. Right? So this is the equation for this. Rho equals 2 cosine of phi. Right? So what does our shape look like here? So let's see if I can draw this. Sort of have, let's say this is our normal sphere of radius 1. Then the second one has its center sort of at the top of this one. Right, so we're kind of looking at this region. Now here, our axes look like this. Right, so we're looking for the region inside both of these spheres here. Right? So, what do we got to do to figure this out? Well, we need to think about, well, how are we going to set up these bounds? So here, this is going to work out sort of how we did some problem like this with spherical coordinates, kind of like inside one polar region and outside another one. Remember here, rho measures from the origin outward. So, depending on the value of phi in this case, if it's pretty low, it's going to start at the origin and hit that green sphere until this point here, where the two spheres intersect. Then it switches to the blue one. So, we need to set up the two different parts here. So the question is, well, at this level right here, what is phi? Right? This is where it's going to get cut off at. Well, this actually isn't too hard to do, right? We have rho equals 1 for this sphere. We have rho equals 2 cosine phi for this sphere. We can set them equal to each other and see what that value is. Okay. Tablet doesn't plugged in. All right. So if we set them equal, we get 1 equals 2 cosine of phi. So cosine of phi is 1/2. Right? And phi here then is let's see here. To make cosine equal to 1/2, we want phi equals pi over 3. Right? So it's saying falling all the way down to here, it's pi over 3. Okay. So the volume of this shape That's what we're computing, yeah, the volume. Right, so again, we're always doing integral of dv. So we have to compute this volume in two pieces. Right? The piece that ends on the blue sphere and the piece that ends on the green sphere. So let's get our usual rho squared sine phi. D rho, let's say d theta d phi. So for the blue sphere part, the bounds are pretty easy. It always starts at the origin and it goes to 1. Right? Theta, well, we have the full 360 rotation of this shape again. So this is going to go from 0 to 2 pi. Right? Where we go all the way around the z-axis for this one. And then d phi, well, this is our bound here. Remember, the very top on the z-axis is when phi equals 0, and then it increases as you fall down. So this is going to go from 0 pi over 3. Now this is sort of the blue part. So I'll just put a little blue bracket on it like that. Right. Now we want the green part, this one. So again, rho squared. Give it a little more room this time. Rho squared sine phi. And I'm going to do d rho d theta d phi again. Right, so this is for the part that ends on the green sphere. Right? So when we're ending on the green sphere, again, we're starting at the origin and moving out to that sphere. So it goes from 0 to 2 cosine of phi. Right? All good. Theta, again, just like last time, is going to go from 0 to 2 pi because we have the full shape. And one more, phi. What does phi do? So it should pick up where this one left off, which is pi over 3. Where does phi stop? Well, phi stops where this sphere hits the origin here. And it turns out that, well, that means we need rho equals 0. If we set rho equal to 0 here, we need cosine of phi is 0, which is pi over 2. And there we go. So the volume in this case has to be split up into two pieces, but it's a lot simpler than trying to do this in other coordinate systems. Right? Because you could set this up in cylindrical, but if you set it up in cylindrical, you're going to have a bit of a tougher integral to compute. Right? So yes, this splits into two pieces, but the two pieces are pretty simple. Okay. So that's it for our first session here. We'll go back through these 4 problems in just a little bit. All right. Let's do a few problems here. Good afternoon. All right. So, I just have 4 problems here for this stuff. Just wanted to kind of go through and show how we can sort of switch between different coordinate systems. And for these, I really just want to spend time setting up the integrals. Once you've set them up, then, there's not that much to actually compute them. So let's just go ahead and get started here. Problem 1. Problem 1 here. So problem 1 just says evaluate this integral. Right? This integral being the integral from 0 to 2 square root of 2 minus square root of 8 minus x squared to square root of 8 minus x squared, integral from minus 1 to 2 of 1 plus x squared plus y squared dz dy dx. So we want to integrate that thing. Now, it is possible to do this in Cartesian coordinates without switching to a different coordinate system here, but you'll find it's probably not that fun. You'll have to do a trig substitution to do the y integral, and then the x integral probably just going to be disgusting. Not sure offhand what it would be. But it is possible if you're diligent enough. But I don't want to do all that work when I can do a lot less work. To do that, we need to start switching this integral here to a different coordinate system. And to decide what to do, it's a good idea to look at what the shape is that we're integrating over. Right? What is the region of integration here? So what I'm actually going to start with is, let's look at, since z is the inside integral here, I know z just goes from minus 1 to 2, so it's a pretty simple shape in the z direction. Let's look at what this is in the xy plane, because whatever the shape we get in the xy plane is just going to sort of translate up and down for the z direction. Right? So let's start with this. Let's write out what all our bounds are here. So these bounds are for x. So 0 is less than or equal to x is less than or equal to 2 square root of 2. Right? This one here says y is between negative square root of 8 minus x squared and 8 square root of 8 minus x squared. And we'll write the one for z as well. Right. So this is what it says we're working with here. So now, what are each of these graphs telling us? So again, let's just focus on the xy plane stuff for now. Y, x. So here, the x things are telling us, let me put a 2 square root of 2 right here. The x values are telling us that we're stuck between here and here. Right, so this is x equals 0 over here. This is x equals 2 square root of 2. Okay. What do these equations tell us? Well, if you recognize, hopefully you do, what these are, this is the top half of a circle. This is the bottom half of a circle of radius square root of 8, which is 2 square root 2. So let me even say, let's put the bottom half of it in green, top half in blue. Then say this is 2 root 2 up here, and these are the negative versions. Then we're looking at this shape. Now, if we want to say, all right, y is stuck between these two things, x is stuck between these two red lines, we're looking at this semicircle here, right? This half circle. That's the region in the xy plane that we're integrating over. In other words, that's the shadow of this shape that this triple integral is being done over. That's the shadow of it in the xy plane. So here I try to do this in 3D Sketch. So the 3D shape, give it a go. Some kind of like half cylinder. Where, say, put these axes right here, the z-axis this way, the y-axis is that way. Actually, the way I drew it, x-axis should actually come directly out. So this perspective's a little bad, but so this cylinder dips a bit below the xy plane, right? It goes down to z equals -1. And it goes all the way up to z equals 2. Okay. So hopefully that's kind of understandable. But imagine we have a cylinder and we cut it in half long ways. And the cylinder should be height 3. That's from -1 up to 2. The nice thing about switching from from Cartesian to cylindrical is z doesn't change. Okay. So since our region here is a cylinder, we probably want to try cylindrical coordinates on it. Right? So that's why I was saying, when we switch to cylindrical coordinates, it's kind of nice because z can stay exactly the same. Okay. So how do we start describing this region in cylindrical coordinates? So so we need to say, let's call this region D. So if we're trying to describe this in terms of r, theta, and z, well, the r and the theta part of this are going to be determined here in the xy plane, right? And then z is just going to do whatever z is going to do. So in this case, r, if we look at r, it's going to go from 0 to 2 square root of 2. Right? If we look at theta here, we want to go from sort of the negative y-axis, we want to measure all the way around to the positive y-axis. So that should tell us that theta goes from negative pi over 2 to pi over 2. And again, z doesn't change. A little squished in there, but readable. One z, listener 2. Right. So that's our nice region of integration. So these bounds, really just this bound in particular is kind of bad. But they all become constants in cylindrical coordinates. So let me call that integral I up there. So I can rewrite it down here. Right? So the square root of 1 plus x squared plus y squared, what is this going to turn into? Well, Now again, this is just polar coordinates with a z tacked on. So x squared plus y squared is still r squared. So this is going to be square root of 1 plus r squared. The dv part, the dz, dy, dx, right? We get our extra r like we normally do for polar coordinates. And then we just have to decide, well, what order do we want to integrate in? Right? And since all of these are constants, it literally doesn't matter. Right? Fubini's theorem says if all your bounds are constants, you can flip them around at will. So let's just say, I don't know, dz, dr, d theta. May as well leave the z the same, right? Minus 1 to 2. R, we said, goes from 0 to 2 root 2. And theta, so minus pi over 2, pi over 2. Right? So again, I think I'll avoid actually writing out the computation of this integral because it's not going to be that bad. You'll have to do a u substitution for the r integral, but it's not so terrible there. I think I did work this out earlier, and this wound up being like 2 pi or something. But again, these problems, again, the most interesting part of this is switching the bounds, are setting up the integral in such a way that it can be computed. Right? So again, this isn't too bad here. Any questions about this one at all? So let's look at the next problem here. Problem 2. Right, so in problem 2, we are trying to find the volume. Why does this happen? Okay, apparently double tap means zoom in by like 5 times. All right, so we want to find the volume between the cone, z equals square root of x squared plus y squared, and the paraboloid, z equals 12 minus x squared minus y squared. So when we look at these, we want to figure out, all right, well, how do I want to set this up? What coordinate system do I want to use? Right? So when you see something like this, a cone is actually quite nice in spherical coordinates. It's not that bad in cylindrical coordinates, but it's really nice in spherical. However, a paraboloid is not so great in spherical, and it's quite nice in cylindrical. So in this case, we'll want to stick with cylindrical coordinates for this one. And I reproved that fact to myself in the first session when I tried to set up the bounds for this in spherical and was like, oh, it's terrible. Probably don't want to do this. Not to say it's impossible, but a paraboloid doesn't lend itself very well to spherical. So you'll definitely want to stick with cylindrical for that. That being said, try it. See what you can get if you try and do this in spherical. All right. Anyway, so to do this in cylindrical, we'll want to convert these equations to cylindrical. Okay? So again, we're going to use x squared plus y squared equals r squared. Then this one turns into z equals square root of r squared. This one turns into z equals 12 minus r squared. Right? Now, since we're looking at the positive square root here, we're just going to say that this is z equals r. Right? Z equals r gives us the top half of the cone. If we did use z equals negative r, that would be the cone that goes downward. So now we have these two, and we need to start figuring out, well, how do we set up the integral for these? So the graphs of these things, let me try and do that here. I'll graph this one in blue and this one in pink here. The shape of this cone, this is the nice 45-degree cone. Looks something like this. Let me not fill in any bit of the cone yet, because then the paraboloid is going to sort of start up here. And it's going to hit the cone somewhere. Say in this circle right here. So this intersection here is what we need to find. Okay. So the cone opens upward, the paraboloid opens downward because it has the negative x squared minus y squared part. So, and if you're interested, the axes are something like this. I often find it easier to just try and draw your 3D shape first and then add in the axes afterward if you want them. It'll look something vaguely like this. Right? So if we do the z integral first, the bounds for z are pretty straightforward. The paraboloid's on top, the cone's on the bottom. It's the other stuff that we have to figure out. To figure that out, we just need to look for the shadow of this shape in the xy plane. Right? This should feel pretty similar. In fact, I think we did on Wednesday. Is that right? No. Tuesday. We did an example of finding the volume between a paraboloid and a cone, except I think the cone was on top, the paraboloid was on bottom that time. So you might remember we did something similar to that. Right, so here I can take these two shapes here, these two equations, and I need to figure out, well, what is this intersection here? Right? So to do that, I can, do what we did that last time and solve for z. That tells me how high up it is, and then plug that back in. And I think I actually did that in the earlier section because I didn't convert these right away. But here, really what we need is r. We need to know how big r gets. And we can use these two equations and solve for r. Right? Just plug one into the other. So plugging this in here, we're going to get r equals 12 minus r squared. If I want to solve this, I have r squared plus r minus 12 equals 0. So I can factor this. I almost wrote x. R plus 4, r minus 3, 0. So I get two things. I get r equals negative 4, and from here I get r equals 3. So which one of these do you think we want to use? Yeah, exactly. We want the positive value here. Because again, this cone, this is the top half of the cone. If we pick the negative r, then z is going to be negative 4, which is, all the way down here. What this negative value represents here is the intersection of this paraboloid with sort of the other half of this cone. Right, so if we had z squared equals x squared plus y squared, we'd get a cone that opens up and down. It would kind of be like an hourglass shape. And that's what this negative 4 is. But we don't want that one. We want this one. We want that one. Right? because that's going to represent this value. So what this means then, in the xy plane, the shadow of this shape, right, if we look at this, we're going to have the full sort of 360-degree shape here. So the intersection in the xy plane is going to be our full circle of radius 3. Right, so when we're setting up the bounds for x and y, we get the whole disk here. So when we try and do the volume of this, and again, we'll just set up the integral for the volume, and we won't actually compute it. Right. So the volume, again, volume is always triple integral over your shape of dv. Right. So dv turns into r, and then we need to decide what order to integrate in. So here, it's a good idea to integrate, well, we have to integrate z before r, unless we want to solve these for r. So let's just do z first then. Right, so the top shape is the paraboloid. So we get the 12 minus r squared on top. The bottom shape is the cone, so we just get an r on the bottom. And then the other two, it actually isn't really going to matter the order. So we'll just keep the usual dr d theta order. Okay. Since we have the full disk here, r is going to go all the way from 0 to 3, and theta is going to go all the way from 0 to 2 pi. That's it. Okay. So again, you can try and set this up in Cartesian coordinates, and you would end up with something kind of similar to these bounds here. And it just wouldn't be that fun to try and do in Cartesian. Might be possible, but I don't know if Any questions about this problem? Awesome. So, in problem 3 here, so we're trying to compute this triple integral of x squared plus y squared z squared to the minus 3/2 dv, where d, this is the region in the first octant, between the spheres x squared plus y squared plus z squared equals 1, and x squared plus y squared plus z squared is 4. Right? So the problem actually says between the two spheres of radius 1 and 2 centered at the origin. Those are these two right here. Okay. So if we look at this problem here, right, we want to try and figure out what coordinate system to use. So there's two ways to see what the better choice is here. The first being that, well, the regions here are bounded by spheres. Sounds like a good candidate for spherical coordinates. Another thing is, notice here we have, x squared, y squared, and z squared. Right? X squared plus y squared plus z squared. That's exactly rho squared. Whereas up here, okay, this turns out to work out nicely in spherical. This doesn't, because x squared plus y squared, we have those two, but there's no z squared. In this one, if we square both sides, there's at least x squared, y squared, and z squared, even if this, has the wrong sign. For the paraboloid here, we're just kind of, out of luck. So that's another good way to try and help decide between the two is, do you have x squared, y squared, and z squared, or sort of just x squared and y squared? So in this case, we have all three. And they're spheres anyway, so this is a good candidate for spherical. Okay. So in spherical coordinates, right, this sphere of radius 1 is given by rho equals 1, because rho squared is x squared plus y squared plus z squared. This sphere here is rho equals 2. All right. So now we have to start setting up this integral here. So again, let's call this I. So so this part here, the actual integrand, right, we just need to convert that to spherical. Again, remember, x squared plus y squared plus z squared is rho squared. So this is rho squared to the minus 3/2. And then dv, well, dv is rho squared sine phi. And then we need to decide on an order of integration. So it's going to turn out to not actually matter for this problem. Right, so let's go ahead and do rho first, so we can stick ourselves between the two spheres. The inside one is 1, the outside one is 2. So the bounds on rho go from 1 to 2. Right? And again, remember how rho works. Right? Rho works similar to how r does in polar coordinate. Now remember, in the 2D plane, you visualize r as starting at the origin and sort of expanding outward. Right? That's exactly how rho functions in 3D space. It starts at the origin and it grows outward. Right? So as it's growing outward, the first thing you hit is the sphere rho equals 1, and then it keeps growing until you hit the sphere rho equals 2. Let's do the order d theta d phi. So one thing that's maybe a little unfortunate is at least intro calc books do this, but maybe it's true in general. Math and physics have opposite conventions for what theta and phi mean. This is a little unfortunate. But for us, theta is going to mean the angle sort of around the z-axis. Right? So if I want to stay in the first octant, right? So my theta value is still going to sort of start measuring. It's the exact same theta from polar coordinates. Put it that way. So it still measures from the positive x-axis and then moves counterclockwise around. So if I want to stay in the first octant, what do you think my bounds for theta should be? Remember, the first octant is above the first quadrant in the xy plane. Yep. Pi over 2. So that makes sure that we stay in the place where x and y are positive, up in the first quadrant. All right. Now we need the bounds on phi. Now, here's another thing where there's differing conventions. And let me double check our textbook. And see if we're using the same one. Because I didn't even think about that until right now. Oh, good. We're using the same one. Some calculus books use the other convention. So the way we measure phi starts, phi equals 0 starts you vertically upward. And then as phi increases, your angle falls. So we would start at phi equals 0, and then phi equals pi puts you down at the negative z-axis. And that's all we need. Another convention is to start phi equals 0 in the xy plane and go from minus pi over 2 to pi over 2. Really depends on sort of what you want to do there. But then this part will change. All right. So if we want to stay, again, in the first octant, we need to stay above the xy plane. So I'll give you a second to think about what phi has to be. Again, remember, phi starts vertically upward and then falls away from the z-axis. So what what values we're just looking to stay above the xy plane. So we should start at 0 because the z-axis is above. I heard myself more than you, but I assume this is what you said. But yeah, so starting at 0, we're up top at pi over 2. We're in the xy plane, so we want the stuff from 0 to pi over 2. And then there we go. There's our integral written in spherical coordinates. Not too bad. This... I'll do the step of simplifying what the integrand looks like. So this is going to be rho to the negative 3 times rho squared. So it'll simplify to something like this. And at this point, it's just, all right, here's a triple integral. Go ahead and compute that. So there's nothing too special going on here. So any questions about this one at all? Excellent. All right. So problem 4, this one's a little more interesting. Normally I would do sort of a cone and a sphere problem, because those are kind of interesting, but we have one of those in the lecture videos, so I'll let that video talk about that. Instead, what I want to do here is an example where we find the volume inside these two spheres. X squared plus y squared plus z squared equals 1. And x squared plus y squared plus z minus 1 squared equals 1. So I want the volume that's stuck between these two spheres. So I'll say this one's the blue one and this one's the green one. These two spheres, so this one's centered at the origin. One sphere. Right. This sphere is the same radius, but it's shifted up by 1 unit. So the bottom of this sphere is going to be at the center of the blue one. The center of the green sphere is going to be at the top of the blue one. So these spheres are supposed to be the exact same size, but I'm bad at drawing. Right, so we're sort of looking at a situation like this. Here's, say, the x-axis, y-axis, z-axis if you're so inclined to draw those in. Right? So we're looking at the region, this kind of there's a good name for this shape and I can't think of it. It's almost like I'm going to call it a UFO. It's not, but I had a better name for that shape and I forgot what it was. Yeah, it's kind of round on top, round on the bottom, and then kind of sharp on the edges. Yeah, so we need to figure out how to find the volume of this thing. Right? So the fact that these are spheres is a good indication we might want to use spherical on these. This equation, this bottom sphere, the blue one, is going to be given by rho equals 1, which is simple enough. This one, on the other hand, this sphere is off-centered, so maybe we get something a little bit different here. Right? So let's convert this to spherical first. So to do that, I recommend multiply this part out. Right? And let's start switching pieces here. So again, we know x squared plus y squared plus z squared. We know that's just a rho squared. Minus 2z. Well, that's, remember, z is rho cosine of phi. And then I want to simplify this equation as much as I can. And there's a 1 on both sides here, so let me just cancel those so that this equals 0. And here, I can divide by rho to cancel those. And then I'm going to move the 2 cosine phi to the other side. And so I'll write in green here, this is rho equals 2 cosine of phi. So hopefully that kind of reminds you of circles in polar coordinates, right? If we had that circle that was off on the x-axis, that was, you know, r equals cosine theta or something like that. A similar kind of deal going on here. All right, so how do we find out how to set up the integral for the volume of this thing? Right? Now, if we're going to do this in spherical coordinates, though, it's important to remember how spherical coordinates measure. Okay? So, you know, it looks like, oh, hey, the blue one's on top, the green one's on bottom. True, but that's irrelevant for spherical coordinates. Right? For spherical coordinates, we're measuring from the origin outward. So hopefully this picture doesn't get too terrible here. So starting at the origin, if we're moving out, we're going to hit the blue sphere for a while. Okay? Until sort of this spot right here, where the two intersect. And then, as we move from the origin outward, we're going to start hitting the green sphere. Okay? So hopefully this reminds you of, we did that example in polar coordinates on Tuesday about the area inside two circles. It's going to be just like that. We're going to have a very similar thing there. Except it doesn't have to split into 3 pieces this time. There's only 2, which is nicer. Okay. So what I'm going to do is say, all right, well, the volume is always this triple integral of dv. And here, this is going to split into 3 pieces. Or sorry, 2 pieces. I don't know why I said 3. Probably because there's 3 integrals. All right, so let's figure out how to set up these integrals. All right. So let's say the part that hits the blue sphere is the first one. The part that hits the green sphere is the second one. So it's probably a good idea, since really the big difference here is where rho is starting and ending. Let's do rho first. So we'll do rho first in both of these. So when we're hitting the blue sphere, when we're starting at the origin and we're still hitting the blue sphere, the bounds are going to go from 0 to 1 on rho. In the second integral, I'm still starting at the origin, so the bottom bound is 0, and I'm hitting that green sphere, so the upper bound is going to be this 2 cosine phi here. Hopefully that makes sense. Because it's easy enough, let's do theta next. What seems like a good choice for theta? Think about the shape of this intersection here, of this solid. And think about what makes sense for theta in this case, the bounds on it. So this shape goes all the way completely around the z-axis. We have that full rotation there. So this is going to go from 0 to 2 pi for both of these. Right. Again, we have that full solid and it goes all the way around. So that leaves phi. So this is the fun one. Right? So for the blue sphere, remember, phi starts up here and then sort of falls. That's what phi does. So since at the very top we're on the blue sphere, phi is going to start at 0 there, but where it ends is at this intersection. So we need to know the phi value here at the intersection. We can do that pretty simply by just taking the 2 equations that we have and setting them equal to each other. So we're solving. That's too far for phi. Phi at its maximum is going to be just pi. But here, to figure out where it should actually cut off at, we set these 2 equal to each other. So that says cosine of phi has to be 1/2. And cosine of phi equals 1/2 at pi over 3. Right? The other value, which is 5 pi over 3, is too far out of the range. Sorry. Right, so phi for this integral will start at 0 and fall to pi over 3. That's when we're going to hit that intersection. That means the second integral picks up at pi over 3. And then what does it end at, though? what is the bottom of the sphere given by what phi value? In other words, when is row 0? So if you set 2 cosine phi equal to 0, we're asking, well, when is sine of phi equal to 0? That's going to be at pi over 2. And so now we have our two pieces. So if we compute these two pieces and add them together, that's going to give us the volume of that solid between the two spheres. Right. So again, neither of these. Sorry, why I'm yawning so much today. Yeah. So looking at these two integrals, they're not that bad to compute at this point. The second one might require a substitution of some sort, or there's a few ways you can do it. But yeah, so neither of these are really all that bad. Right, so any questions at all about problem 4 here? Again, I think the most important part of these types of integrals is being able to set them up. I think you got a little bit of lag. That's fine. But yeah, it was pi over 2. Okay. So, yeah, so let me just say one more time. Any questions about this one or any of the 4 problems we did? Excellent. So hopefully, this helped out a little bit, making sense of how these coordinates work. Give you a little bit to go off of. Of course, let me know if you have any questions. With that, have a good afternoon. See you guys on Monday.